So this one's pretty straightforward. The opposite of hydrolysis is condensation, right? Most people got that correct. So who wants to just remind us what hydrolysis is? It's pretty straightforward. It's in the name. So adding water to break a covalent bond, right? So hydrolysis versus condensation is where we give off water to form a bond. Okay. All right, so let's see what we did for this one. The site of oxidative phosphorylation, this person said B. The answer is C, so it's across the inner mitochondrial membrane, not the mitochondrial matrix, right? The mitochondrial matrix is the center within the inner mitochondrial membrane, so it's across that membrane that it's. All right. Okay, so this one's asking about the activation energy. So a high activation energy is going to have what type of rate of the reaction? Right? Most persons said B, and that's correct. So a high activation energy, meaning that it takes more energy to get the reaction going, so it's going to proceed at a lower or slower rate. And the opposite is true. Okay, we got B here. B is correct. So an enzyme lowers the activation energy, makes the reaction more favorable. All right, so let's see, an endogonic reaction. There is, some said A, some said B. So more energy in the products than the reactants, right? So they, versus an exergonic reaction, which is proceeding in the opposite direction, right? More energy in the reactant. Okay, everyone get this one? Any questions here? All right. All right, so cellular respiration, glycolysis, and the products of glycolysis. All right, so the products of glycolysis, right? Majority said D, and someone said E, but D is correct, right? So 2 pyruvate, 2 ATP, and 2 NADH. Now, bear in mind, if this word net was not here, this would be incorrect, right? This net, because it's actually 4 ATP. So look out, make sure that net is there, and that you're clicking the correct amount. All right, so let's see what we got here. All right, good. Well, everyone said C. So a concentration gradient is responsible for the chemical driving force, right? All right, so let's see what we did for this one. Okay, so we got a split and most persons said B. So let's discuss this a little bit. So this is asking which statement is incorrect when we're talking about the electrical driving force. So let's look at each of the statements. A is saying for a solute that is uncharged, the electrical driving force created by the membrane potential is 0, right? This is true. Remember we said the electrical driving force has to do with the charge on the particle. So an uncharged particle has no electrical driving force essentially. It's not going to move in either direction. There may be a chemical driving force based on concentration gradient, but no electrical force, right? So that's 0. B is also true. A membrane potential of -70 will exert a larger electrical driving force on calcium, which is divalent, than on sodium, right? Can anyone say why B is correct? No, so calcium is not negative. Calcium is a cation, but it's divalent, meaning that it has 2 charges, right? In its outermost shell. So as opposed to sodium, which is a monovalent ion, it's going to have a stronger electrical driving force because it has 2 positive charges on it. Okay, so that is true. So B is a correct statement. C is an increased or more negative membrane potential will exert a greater electrical driving force inward on a monovalent cation. This is true, right? If we have a greater membrane potential, there's a greater separation of charge, and so a positively charged anion, I'm sorry, that was contradictory. Positively charged ion, which is a cation, will want to move into the cell with a greater force. Right? so C is true. D is a membrane potential exerts a greater inward directing driving force on anions than on cations. Is that true? So the inside of the cell is more negatively charged. The outside is more positively charged. Will particles want to move inward or outward? They're an anion, let's say. Anions are negatively charged. Cations are positively charged. So they're going to want to go outwards, right? So D is incorrect. It's going to exhibit a greater outward force on anions rather than cations. All right. So D was the incorrect statement there. Okay. Okay, so let's see what we got here. Right, most persons said D, which is correct. So simple diffusion does not rely on active transport. It relies on the surface area and the driving force and the permeability to the membrane. Okay, so D is correct. Okay, so let's see. We got D. So D is correct. Which of the following does not influence the rate of facilitated diffusion? So facilitated diffusion requires a carrier, and so the solubility of the membrane is not important. Whether or not it's lipid soluble or hydrophilic or hydrophobic is not important because we have a carrier. All right, let's go on to the next. Okay, so we got a split between A and D. How do active and passive transport differ? So active transport requires the molecules moving to have energy, while passive transport does not. And then D was active transport works against the electrochemical driving force, while passive transport works with it. Okay, so D is not necessarily correct. Or D is correct, sorry. A is not necessarily correct, right? So active transport works against the electrochemical driving force. I'm going to remind us what the electrochemical driving force is. Let's go back to this one. This is the gradient that a molecule wants to move against, right? Active transport is going to require energy because you're moving against that natural driving force, right? Whereas passive transport, we're working with the electrochemical driving force. So the molecule is moving in the direction that it wants to, okay? So we don't require energy. Let's go here. All right, let's see here. Most persons said C, which is correct. A cell in a hypertonic solution will shrink. Right? Keep moving. All right, let's see what we got here. Okay, good. Most persons said B. So the sodium potassium pump is correct here. Okay, let's look at our responses. This one is pretty straightforward. Good. So A is correct, the resting membrane potential. Okay, let's see what we got. All right, so most persons said C. The question here is, which of these is not a direction in which the chemical, electrical, and electrochemical forces push or pull potassium? Right, so A is true. The chemical driving force of potassium is to move out of the cell. B is also true. The electrical force of potassium is to move into the cell. Right, remember potassium is positively charged, the inside of the cell is more negative, so it wants to go in. The sum total of those two forces, which is the electrochemical, is going to be in what direction? So the sum total of the electrical and the chemical moves in what direction? Out of the cell, correct. So that eliminates D, and C is true. Right, so the correct answer here will be D, which is the incorrect statement. Right, so it's asking about the incorrect statement. So the answer is D, right? All right. All right, so let's see what we got here. Most person said C, which is good. C is correct. So during repolarization, the permeability of potassium is going to increase as the membrane potential becomes more negative, and the permeability of sodium decreases, again, as that membrane potential decreases. Right? Does that make sense?
Yeah, I read it wrong. I just thought it said depolarization.
No, repolarization. Yeah, so the downflow. Make sure you read your exam questions carefully, guys. It's easy to miss. Okay, let's see what we got here. This one is pretty straightforward. All right, good. D. So there's both spatial and temporal summation for graded potentials. Okay, good. C here. It's very straightforward. Calcium. Okay, so this one's asking about the receptors that cause fast versus slow responses at the postsynaptic membrane. So most persons said C, which is good, and that is correct. Fast is ionotropic receptors versus slow would be your metabotropic receptors, right? Remember, these have to be coupled to a G protein, whereas these are a channel in themselves. Okay, let's look at this one. Right. Most persons said A. The difference between excitatory EPSPs and IPSPs is that EPSPs depolarize, whereas IPSPs hyperpolarize. Right, that is correct. All right, let's see what we got here. So presynaptic facilitation. So we have most persons saying D. And the correct answer here is more neurotransmitter is released and the cell is less likely to fire an action potential, right? The postsynaptic cell. Right? All right, so let's look at this. So most persons, got an even split. In the spinal cord, where are the white matter and gray matter found? So if you took a cross section of the spinal cord, we'd have white matter on the outside, which is myelinated, and then gray matter, which is unmyelinated on the inside, right? All right, so let's see what we got here. So the blood-brain barrier. Good, astrocyte. So D is correct. All right.
Well, there's 30, there's 31. 62.
All right, so we're going to go through a few from the second half here. All right, so we have a few more from the second half of the semester. Let's go through these, see how many of these we get through. All right. Let's see. All right, so although someone said D, the correct answer is B, which is rest and digest. So not twist and shout. Okay, so this question asks about the anatomy of the parasympathetic system. And most persons said A, some said C, right, which is the sympathetic. division, but A is correct. So brainstem and sacrospinal cord. All right, let's see what we got here. So the path of parasympathetic signal from its origin to the effector tissues, B. So a ganglia, which is closer to the effector organ, and then to the organ, right? So you have a longer preganglionic neuron and a shorter postganglion. This person said D. So A is correct. So this is specifically the toxin acting at the neuromuscular junction. So it's only the somatic nervous system. Tuberculare is that toxin we talked about, the curare toxin. Remember latroxin, those other toxins we talked about. So this one's pretty straightforward. So let's move it right along. So the correct answer here is B, a tendon. Right? A ligament connects two bones. So bone to bone is a ligament, muscle to bone is a tendon. All right, another very straightforward one. All right, so the long fibrous molecule that covers the actin monomer is tropomyosin, okay? Whereas troponin is the other regulatory protein associated. All right, so C here was correct. We have the actin binding site and then the ATPase site. Okay, so most persons said said A. A is correct, which is the area of overlap, the A band. We know the I band is only actin, the Z line is the end of actin, and the H zone is around the M line, which is only myosin. Okay, so what happens during the power stroke? Oops. Okay, so most persons said A, which is correct. So myosin is doing the pulling, and it's pulling actin towards the middle of the sarcomere, towards the M line. All right, so the answer, oops, let's get that. The answer here was B, binding to troponin. Now this question should have specified skeletal muscle, right? But that's understood. So if it was skeletal or cardiac, this would be true, but for smooth muscle, this is not true, right? Let's move on. Okay, so let's have a look here. All right, so D is correct, the presence of gap junctions in cardiac muscle. Right, they both have striations, they both have sarcomeres, and they're both regulated by troponin and tropomyosin. Okay, so quite a few people said B, which is not correct. So I don't want to confuse you, but it's not correct because it's correct. Right, so B is a true statement. Right, so the answer here is D. So smooth muscle is regulated by autonomic neurons. It does have thin and thick filaments, but they're obliquely arranged as opposed to running parallel, the way the sarcomere is organized. C is correct. So it does have tropomyosin, but it's not regulated using tropomyosin, right? It's regulating with calmodulin. D is incorrect. So calcium signal that triggers cross-projectivity targets actin. That's not true. The calcium signal in smooth muscle targets what protein? It's not actin, it's myosin. So it's the myosin head. If you remember, MLCK phosphorylates the myosin head. So it targets myosin and not actin. So cardiac and skeletal muscle, calcium targets actin, whereas smooth muscle, calcium targets myosin. All right, let's see how many more of these we get through. So let's aim for 2 more, and then we'll call it a day. Okay, let's see what we have here. So why can't cardiac muscle achieve summation? Because of the length of the action potential. So the action potential lasts for quite a while, and so there's not that opportunity to depolarize the cell again. All right, let's look at one more. Pretty straightforward. All right, so the chambers, the large chambers of the heart that pump blood are going to be the ventricles, right? So the ventricles are pumping, the atria are receiving, right? So that's the correct.